Welcome to my PhenoRob Pills lecture, Causality without randomized experiments, from potential outcomes to causal machine learning. What I would want to talk about today is how we can answer causal questions if it's not possible to run randomized experiments, so how we can answer causal questions from observational data. And I will also try to explain why that is relevant and important for us in PhenoRob. Specifically, the aims of this lecture are that I want to provide you an understanding of why causality matters for PhenoRob, so why causal questions matters for PhenoRob, why randomization is useful but not always possible, so why there are cases where you cannot run a randomized experiments, and what the challenges are associated with this, so why it is challenging to answer causal questions from observational data without randomized experiments. And I would also want to provide you with an intuitive understanding of key methods that can be used in this context or for that purpose. And I've listed the methods here that consists of more classical econometric methods, but I will also try to cover the last two here, more novel approaches that leverage methods more from the machine learning area in order to answer causal questions. To start this off, I want to start very simple, providing you examples of causal questions and also try to highlight why causal questions are important for PhenoRob. One example of a causal question that is very famous or very important in agriculture is how does N fertilization affect yield? Another example of a causal questions more from the medical area, something that we have grown very used to in the last 2 years, is the question, what is the effect of vaccination on hospitalization? Also a causal question. Or from the economic area, a question that is very famous in developing those approaches that I will present in the following, what is the effect of the minimum wage on employment? So this all are examples of causal questions. And also in PhenoRob, we pose causal questions. And for this, I want to draw your attention to PhenoRob Objective 4, which says that we want to investigate and assess the technological, ecological, and economic feasibility of new farming system enabled by novel technologies. And that's the relevant part or the important part here, determine their ecological and economic impact. So this later part really is a causal question. So expressed simply, the causal question is, how does technology affect environmental or economic outcomes? Yeah, so this is really the causal question that we want to answer. So causal questions are fundamental, are core to achieving the objectives posed in PhenoRob. So these are all examples of causal questions, but they are quite different in the way that we can address and answer them. If you think about the first two questions, if you were asked to answer those questions, then you would probably answer those questions using a randomized experiment. And you see here for the first question a picture that some of you might recognize. So this is a picture of a randomized field trial used, for example, to answer that research question. So what you would typically do to determine the effect of N on yields is that you would design an experiment, split a field into smaller parcels, randomize treatment, and then record the yield effects depending on treatment, and from that calculate a causal effect. Similarly, for the second question, if you would want to answer that question, what we typically do is that we run a clinical trial where you split your population in a treatment group and a control group, randomize treatment, so to say, and then record the outcome from the treatment group and the control group. Yeah. So this is basically answering causal questions with the randomized experiments, when randomization, a randomized trail is possible. However, if you think about the third question of minimum wage unemployment, here, obviously, it's not that simple to set up randomized experiments. Conceptually, it would be possible that we would randomize the minimum wage across regions and then record the outcomes. However, setting policies is obviously not something that is typically possible in a PhD thesis. Yeah? So usually we as researchers cannot answer such a question by running a randomized experiment. So even though these are all causal questions, the way we can answer them differs quite substantially. And to answer such a question, we therefore need to rely on other methods, for example, on methods using observational data to answer causal questions, which is the core of that lecture. What about the PhenoRob question? How does technology affect environmental or economic outcomes? Well, some of these aspects can probably be answered in a randomized experiments. And you see here the image from the patch crop experiment, which is a large-scale randomized trial used to answer some of that, or some aspects of that question in a randomized experiment. However, there are limits to randomization. Yeah? So particularly in CP6, we want to study technology usage on farms, and the technology usage on farms might differ from research stations. And we would particularly be interested in studying how farmers used technology under market conditions. Additionally, it's impossible to force farmers to use a technology. That's usually not what we can do as researchers. So we cannot randomly assign technologies to farmers and then record the outcomes. There might also be secondary effects of technologies that we want to study, which is quite difficult in research stations. So there are other possible reasons that limits the way we can use randomized experiments for answer that question. Yeah. So also for the PhenoRob question, it is important that we have other means than randomized experiments for answering causal questions. Yeah. So I hope that provides the motivation for this lecture to see that causal questions are important and that we need to have ways to answer causal questions beyond a randomized experiment. So one important concept for answering causal questions without randomized experiments is a potential outcome framework, which I want to introduce next. And I would want to do that using a very simple example where we only have two farms, one farm with the technology and one farm without the technology. And we might record an outcome measure, let's say a biodiversity outcome defined in a certain way. And we are interested in determining the causal effect of that technology on this biodiversity measure. We observe that both farms perform differently. So what are in this context the potential outcomes? The potential outcomes are those outcomes that Farm 2, for example, that has a technology would have if it would not have adopted the technology. So it is the outcome of the treated unit if it would not have been treated. And why are those potential outcomes important? Because if we would observe them, then we could easily use them to calculate the causal effect simply by comparing the outcome of Farm 2 with the technology and without the technology and calculate the causal effect. However, potential outcomes are potential, so they are never observed. And that's actually called the fundamental problem of causal inference. We never observe the outcome with treatment or without the treatment at the same time for the same unit. Yeah, so either you have a technology or you do not have a technology. You cannot have both at the same time, obviously. And that's a problem, and that's a challenge for causal inference. What about simply comparing the outcome of Farm 1 without the technology with Farm 2, which has a technology, and interpret that as a causal effect? Well, that might be valid. However, it does not hold in general because we might have selection bias. What is selection bias? Well, it might be that farm 1 and 2 are different from the outset, so that the outcome of farm 2 would have been higher even without the technology. So interpreting this difference as a causal effect is only legitimate if we can rule out selection bias. What does it have to do with potential outcomes? Well, if we would be able to observe the potential outcomes, then we can easily calculate the selection bias and also easily calculate the causal effect. So assume we would have observed, it would be possible to observe the potential outcome, so the outcome of farm 2 without the technology, then we can simply calculate the selection bias, so the difference without the technology between the two farms, the difference between 105 and 100. And based on that, we could calculate the causal effect as a difference between the outcomes of farm 1, farm 2, corrected by the selection bias. So potential outcomes are important for calculating selection bias, and selection bias is important for calculating causal effects. Maybe as an additional example, because selection bias is so important, what is selection bias? It could be that farms are different from the outset. It could also be, or if you consider different examples, selection bias is probably even clearer. So assume, for example, you would want to study the effect of hospitalization on mortality rate. Then, of course, you cannot simply compare mortality rate between people in a hospital and the general population, because you have selection bias. People in a hospital are potentially sicker than the general population. So you cannot calculate, or you cannot derive a causal effect from simply calculating the difference in mortality rate between these two populations. There, it's obvious that we have selection bias, and something that nobody would probably do. In other settings, we also might need to worry about selection bias, even though the selection bias is probably not as clear as in that first example. So consider, for example, the case where we want to study the effect of low tillage on yield, which is something that I will also present later on in an application. Where we might have identified low tillage from remote sensing, or tillage status from remote sensing, and also yield effects from remote sensing, and we would want to derive the causal effect. Can we simply calculate the yield difference between low tillage and high tillage fields? Well, probably we can, but we also here we might need to worry about selection bias, in the sense that farmers apply certain technologies on fields that are different to fields where low tillage application is less likely. So, for example, farmers might apply low tillage on low yielding fields in order to save fuels, but not on high yielding fields. If that would be the case, then also there we would have a selection bias in the technology adoption that would impact our causal effect estimation. So these are examples of selection bias and the motivation to see why selection bias is important. And it's also, so the problem of selection bias is also the reason why we use randomization, because randomization eliminates selection bias. So it ensures, more technically, that the outcome Y and the treatment W is independent. So the outcomes would be yield, W would be low tillage, for example. And that's how we denote that technically. And if that is the case, then the causal effects can simply be calculated as the difference in expected outcomes for the treatment unit minus the expected outcomes for the untreated unit, what you see here. So if outcomes and treatments are independent, as they are in a randomized control trial, we can simply calculate the causal effect as a difference between the treated outcomes and the non-treated outcomes, and use that as a causal effect. So in this case, everything is simple and we can easily derive a causal effect. However, as we've discussed before, randomization is not always possible. And there are also options if randomization is not done or is not possible. And that's what I wanted to present in the following. Before going into a bit more detail of the methods that we can use in those cases, I want to ask you to think about these two examples and how you would approach them in an intuitive way. So we said if we want to determine the effect of hospitalization on mortality, we need to be worried about selection bias, so we cannot simply compare mortality rates with people in the hospital to those in the general population. So what you would intuitively do is that you would try to compare individuals with very similar characteristics in terms of their sickness patterns, their personal characteristics, or their health characterization. Once you have achieved this, then you can simply compare the outcomes between the people in the hospital and not in the hospital. Yeah. Similarly, for low tillage, what you want to achieve is that you're not comparing low tillage fields to high tillage fields, but you want to compare fields between these two treatment states, but with otherwise very similar characteristics. And that's actually the key idea that also these methods aim to involve. More technically, what we say is that once we control for confounders X, so in our example, the sickness patterns, the personal characteristics, or the biophysical characteristics of fields, once we control for them, outcomes and treatment is as good as random as in a randomized control trait. If that's the case, if we can make that assumption, if we are willing to make that assumption, then we can simply compare the outcomes of the treated unit versus the non-treated units, always conditioning on these confounders. So what this expression here really says is that we want to compare the average difference, the expected difference between those observations that are treated and those observations that are not treated, and in both cases conditioning on the covariates, ensuring that we compare individuals that are similar in terms of their characteristics. And that's the basic idea of controlling for confounders, and that's the basic idea employed in the first method that I want to present, which is the matching estimators. So the basic idea of matching is that you match on covariates, so on sickness patterns or personal characteristics or biophysical conditions of the field, in such a way that for each unit I, you find a corresponding unit J of I in the opposite treatment group, which has similar covariate values, and then compare the differences. Yeah, so that's exactly the approach how you would also intuitively approach these problems. And if you do that, if you have these matching units, and that's what you see on the right, you can simply calculate the average effect, the treatment effect on the treated by comparing or by calculating the average difference between the matched individual. One complication or one difficulty or one thing to be done in that case is to define similarity. Yeah? So how do you define if an observation is similar to another observation? And one straightforward way is simply to calculate normalized Euclidean distances in the covariates, in the sickness patterns, in the biophysical characteristics, and use that as a similarity measure. The problem is if you have very many covariates, then you quickly run into problems and things which are not ideal when you do these matching on normalized Euclidean distance. And one alternative, which is very prominently used in that context, is to match on the propensity scores, which basically achieve the same thing. So what you do is you calculate a propensity score, probability of treatment, conditional on controls, and then you can match on these propensity scores, which is basically achieving the same thing as matching on the covariates. You can do a one-by-one matching using the propensity scores, or you can also apply an inverse probability weighting where you give different weights to observations depending on how similar they are in terms of their treatment probability. So this is the first approach, the first concept that can be used to answer causal questions without randomized experiments. And that's useful if you are willing to make the assumption that you observed all confounders that are relevant in determining the outcome and treatment. So the problem is that in certain settings, you are not willing to make this, or you're not able to make that assumption because there might be confounders which are unobserved. So for example, in the sickness example, there might be characteristics of the sickness that you cannot observe, but which matter. Yeah? And if that's the case, then we also have alternatives, and particularly we have alternatives if you have observations across time. So if we have a pre-treatment and a post-treatment observation, and if that's the case, then we can use an approach which is called the difference in difference approach. And the idea is that we compare the difference in the outcomes before and after treatment. So the difference in the blue line here, but adjust for the change in the non-treated units, which is the gray line. Yeah, therefore the name difference in difference. So you basically correct for a common trend. So in the yield example, for example, assume that there is a common trend in the yields, so that yields are generally increasing. Then you would probably want to correct for this trend. Yeah, so you need to make the assumption here that treatment units and non-treatment units behave in the same way, have the same trend, so have a common trend, and of course you need to have a unit of comparison to apply that. This is a second framework that can be used, or the second approach that can be used to answer causal questions from observation data. The third approach, which is very similar to difference in difference in many respects, is synthetic control, and that's useful in a setting where you have fewer observations but rather long time series. And here is an example where we want to determine the causal effect of reunification in Germany on GDP. So you see that development over time, and you could apply a difference in difference approach as described before, where you would select one comparison country and then apply the difference in difference approach. The problem is that you need to select one country, and that might not be ideal because the country that you select might behave a little somewhat differently than the treatment country. And the idea of synthetic control is that instead of selecting one comparison unit, you basically construct a synthetic control country, which is the weighted average of the available non-treatment units. So here the available OECD countries, and you construct this synthetic control country in such a way, so you adjust the weights in that synthetic country such that you match the pre-treatment observations exactly. That's what you see in the right graph. So we've adjusted the weights in such a way that we exactly match the pre-treatment development, and then we can extrapolate the development of the synthetic country as basically the potential outcomes, and then compare the difference between these two lines and interpret that as a causal effect. Yeah? So the synthetic country is really a weighted average of the other countries. So for example, 10% France, 20% Italy, 5% Netherlands, something like that. Yeah? So that's the idea of synthetic control, and that's also a very useful and widely used approach for answering causal questions. These are the three more traditional econometric methods that I want to present, and I also want to present two causal machine learning methods which are more recent. And the first method that I want to present are causal forests. So the basic idea of a causal forest is very similar to a matching approach. So remember, in a matching approach, we said that we want to find individuals that are treated, or for each treated unit, we want to find a non-treated unit which is very similar in terms of the covariates, in terms of the characteristics, in terms of the sickness patterns, for example. And we did that by either matching on the propensity scores or by matching on the Euclidean distance to the covariates. Between the covariates. The causal forest also tries to match observations basically, but it does so by partitioning your sample in a certain way. Yeah, so if you look at one individual tree in that forest, you partition your sample along your covariates. Here in this example, we probably have only one covariate, X, which could be the age, for example. And you partition your sample in such a way that you have 4 bins. And you ensure that in each bin you have treated and non-treated units. And by partitioning in a certain way, you obtain outcomes, or you obtain observations that are very similar in terms of their characteristics, such that you can interpret each leaf that results at the end of the tree as a kind of matching or a kind of randomized experiment, so that you can simply compare the difference in treated and non-treated units within each leaf, with each bin of your partitioning. The key is how you do the splitting and how you grow the trees, and compared to more traditional random forest, you adjust your splitting criteria in a sense that you try to maximize heterogeneity in treatment effects on the one side, and also simultaneously try to improve the accuracy of the treatment effect. So you have an objective function that basically tries to balance two objectives at the same time. And with such a treatment, it can be shown that, or with such an approach, it can be shown that you can interpret the differences between the treated and the untreated units within each leaf as kind of a randomized experiment, and interpret the difference as a causal effect. So that's basically the example for one tree, but you can also, as in a causal of the random forest, combine the results of many trees to get these causal forests. So this is a very a rather recent approach, but which already found quite many applications in economics and environmental or agricultural economics. So it is very useful and already heavily used. One example that I want to present that's also related to PhenoRob topics, and was also presented at the first DigiGrop conference by Jill Dines, where they use causal forests to identify yield effects of low tillage in the US. So what they did is they used remote sensing data to determine yield and tillage status on a very detailed grid level. And then they use causal forests to calculate treatment effects, and that's the result they obtain. And the interesting thing with causal forests is that they, on the one hand, are very capable of dealing with high dimensions in the covariate space. So a high dimension can easily deal with high dimension for the matching approach, so to say. And that they're also very capable in deriving heterogeneous treatment effects. So you're not getting out only an average treatment effect, but you really get out, or you can get out, the treatment heterogeneity. And that's what you see here with the colors. We have, or we can identify regions where low tillage has a high positive yield effect, these red areas, but there are also regions where low tillage has a negative effects. And this is an interesting application, and compared to randomized experiments, the interesting thing here is that we really can leverage observational data for answering that questions from literally thousands of fields, and also cover very long time series, so that they are able to determine the long-term effects of low tillage, and do this across very diverse geographical settings in a way that's probably hard to replicate in randomized controlled trials on research stations. So this is one application. A second approach that I want to present is metrics completion. And for this, I basically want to split, want to change the topic here for one slide and talk about metrics completion and the Netflix prize challenge. And then on the next slide, I will try to explain why that is relevant for our context and for answering causal questions. So if you are familiar with machine learning tools, then you might have heard about the Netflix prize challenge, which is a famous competition on Kaggle, which is basically about building a recommender system. So the problem is Netflix has quite a large number of viewers and quite a large number of movies. but we only have a small number of ratings that users give per movie. Yeah? So if you think about that as a large matrix where you have in the rows the viewers and the columns the movies, then this is obviously a very sparse matrix. And what Netflix wants to achieve is it wants to use the few available ratings a user has given to derive recommendations for all the other movies. So it basically wants to complete these very sparse metrics. And the method developed in that context are matrix completion methods that basically try to derive using algebraic tools, using singular value decomposition to derive a low rank representation of that matrix so that they can which can then be used to complete that matrix. Intuitively, what is done here is that, or you can think about that as you assign movies to types of movies and you assign individuals to the preference for the individual types of movies. And once you have done that, then you can multiply the two together to complete the entire matrix. Why do I talk now about Netflix and matrix completion? If you think about the example that I've discussed in the beginning, these very simple example for the potential outcomes, then it might become clear that the potential outcome problem can also be interpreted as kind of a missing data problem and can be addressed as a matrix completion using matrix completion methods. So that was the example given below, and we said that so the above here is the example given before, and we said in the beginning that we are particularly interested in the potential outcomes, so farm 2 without the technology. If we would have observed that, then we can calculate the selection bias and the causal effect. So this is the missing entry that we need to complete. If you think about that in a slightly larger setup, where you have n individuals observed over t time periods, and we have a staggered adoption pattern, so where we have some farms that never adopt, some farms that adopt late, some medium adopter, some early adopter, then we have that pattern that is given here, where the question marks indicate that this is the potential outcome that we need. So the outcome of a farm, if it would not have adopted for that year, which is 105 in the example above, that we would need to complete in order to calculate the causal effect. Yeah. So it is the problem of potential outcomes is really a missing data problem, similarly as in the matrix or in the Netflix price challenge. And the idea is, and that's what is shown in this paper here, that you can use the matrix completion methods for that problem. And they actually show that it is kind of a combination of the unconfounders approaches, so the matching approaches that I've presented before, and the static control approach that I also presented before. Yeah, so that's a really nice thing about that, is that it basically combines these two methods. So I think this is something very recent and very powerful, and I'm pretty sure that we will see more applications of that in the future. In PhenoRob, we tried to apply that method in the PhD thesis of Elin Martinsen, which is about studying the effect of milking robots on environmental and economic outcomes. And particularly you want to study to what extent there are secondary effects on the farm structure on behavior. We have data for that for Norway, which is displayed here. So we have around 320 or 350 farms in the rows here, and we observe them over several years. What this plot here is indicated is that the black areas are the years where this farm does not have the technology. The green are the cases where it has adopted, and the white things are where the farm is missing due to sampling reasons. Yeah, so we have, in opposite to the previous slide, we have an additional missing pattern here. So that's our data. So you really see that we have these staggered adoption, and we want to apply this matrix completion approach here. And one interesting aspect of the approach is that it can also naturally handle these white spaces, so these missing values that are missing due to sampling reasons. Yeah. So that's what we have, and what we use to apply the matrix completion approach. And we also have results already for that. And what we find is that there are indeed secondary effects which are visible. So, for example, farms adopting a milking robot increase the number of cows, decrease cropping area, or change feeding ratios, for example, and some others. Yeah. So this is the last method that I want to present, and also the example from our work of how we use that methods within PhenoRob. And with this, I want to finish and try to summarize the takeaway messages, coming back to the aims that I presented at the beginning. So I hope I could convey an understanding of why causality, of why causal questions matters for PhenoRob, and particularly for objective number 4. I also try to explain why randomization is useful, but not always possible, because not every treatment can be randomized. And I've also presented the challenges of answering causal questions without randomization, so particularly selection bias and confounders. And I also try or hope that I convey an intuitive understanding of the key methods used in that context. I also want to draw at the end your attention to last year's Nobel Prize, which was awarded to 3 economists which made major contributions in answering causal questions from observational data. And it's very recommendable to read the scientific background on that Nobel Prize, which provides a nice overview about the state and the development of that field of research. Also interesting is to see that there are quite active developments from the machine learning side in answering causal questions. And here I want to particularly point out the Book of Why from Judah Pearl, which addresses a similar question, but with a slightly different view, more from a machine learning perspective. And with this, I want to finish, and yeah, looking forward for the question and answer session and the discussion.